Okay, so good morning, everyone. Welcome to the fourth session of algebra seminar of the Institute of Mathematics and Statistics at Universidad de la República. Today, I'm very glad to we are very glad to have Professor Bernhard Keller from Université Paris Cité. The talk is titled Singularity Categories, Leavitt Path Algebras, and Hochschild Homology. First of all, Bernhard, thank you very much for accepting the invitation to our seminar. It's great to have you here. Whenever you're ready, you can start. Thank you very much.
Thank you very much, and many thanks for the invitation. I'm very happy to speak at this seminar. I will put a link to the notes of the talk into the chat, and you can also read it here. I hope you can see the screen.
Yes. We can see it clearly.
Yes. Yes, so for the in-person audience, you can download the notes here, and for the online audience, I will also put the link into the chat. Yes, so this talk is going to be about singularity categories, Leavitt path algebras, and Hochschild homology. And this is partly based on joint work with Wang, who is now at Taiyuan Normal University in Shanxi province in China, and with Uma Maheswaran Arunachalam from Warangal. And the plan is as follows. I would like to start with a bit of philosophy, namely the philosophy of non-commutative algebraic geometry, as it was popularized by people like Greenfeld and Kontsevich. Then I would like to remind you of the definition of Hochschild homology and extend this definition from algebras to categories and to differential graded categories, and give the basic properties of this extended definition. And then I will look at Hochschild homology of derived categories and of singularity categories of finite-dimensional algebras, and in particular of singularity categories of radical square zero algebras. And then I will apply the results obtained here to get a comparison between Hochschild homology of the DJ-Leavitt path algebra and Hochschild homology of a radical square zero algebra. And at the very end, I will extend this from radical square zero algebras to arbitrary finite dimensional algebras using a recent result by Xiao-Wu Chen and Zhengfang Wang. Okay, so let me start with the philosophical part. So the basic question here is, what is a non-commutative scheme? And there is a historically first answer, which is due to Grothendieck, Gabriel, Manning, and others. And according to this answer, the non-commutative scheme should simply be an abelian category, namely the abelian category of quasi-coherent sheaves on some hypothetical non-commutative scheme or non-commutative space. So we no longer have a space of any type, but we still know about its quasi-coherent sheaves. And then by a theorem of Gabriel, if we know the category of quasi-coherent sheaves on a theorem scheme, then we also know this scheme. So the classical algebraic geometry is embedded into this non-commutative algebraic geometry where schemes are replaced by abelian categories. Yes, so each commutative scheme uses this non-commutative scheme, and the non-commutative scheme determines the commutative one, at least if the commutative one is in a theorem. Now, when we're interested in schemes and this type of non-commutative schemes, we're actually mostly interested in their homological invariance. And then one can observe that the essential homological invariance of this category or the scheme actually only depend on the derived category of quasi-coherent sheaves, not so much on the abelian category itself. And of course, this derived category is no longer an abelian category, but it is still a triangulated category. And this then motivates the second answer due to Greenfeld, Kontsevich, and others, namely a non-commutative scheme should now be a triangulated category, namely the derived category of quasi-coherent sheaves on some hypothetical non-commutative space. So we no longer remember the category of sheaves itself, but only its derived category, because only that is needed for the invariance which we are interested in. And then, in particular, each commutative scheme yields a non-commutative scheme, namely the derived category of quasi-coherent sheaves. And well, now another observation is that there are serious technical problems with triangulated categories. And the most serious one is perhaps that if we consider a functor category with values in a triangulated category, such a functor category is no longer triangulated. Already, if we look just at the index category given by this quiver, yes, so in that case, the functor category is just the category of morphisms in our triangulated category T. And well, if T is triangulated, the category of morphisms in T is no longer triangulated. And well, so we need to replace this with a better technical, with a technically better behaved class of categories. And one solution is to replace the triangulated categories with differential graded categories. Now, a differential graded category actually contains too much information. We need to impose an equivalence relation on the differential graded categories which we consider. And the equivalence relation is derived Morita equivalence. So if we have a DG functor between DG categories, we say that it's a Morita functor if the restriction along this functor is an equivalence in the derived categories of these DG categories. And two DG categories are derived Morita equivalent if they're linked by a zigzag of Morita functors. Okay, and then instead of looking at triangulated categories, we look at Morita equivalence classes of DG categories. So non-commutative algebraic geometry then becomes the study of small differential graded categories up to derived Morita equivalence and of their homological and homotopical invariance, for example, K-theory, Hochschild homology or cohomology, cyclic homology, etc. And so this is the framework in which one should see the results and definitions which I would like to present in the sequel. And well, this looks like a very abstract framework, but actually the categories which we will consider are quite concrete. So here you can see pictures of the type of categories which we will consider. We will not consider exactly these categories, but categories which have very similar properties to these. These are pictures of cluster categories here of type E6, and here a cluster category of type A15. Well, we don't know, we don't need to know what a cluster category is. We just need to know that they are very similar to the singularity categories, which I will consider. Okay, so let's remember Hochschild homology. So we work over a base field K, And we fix a K algebra. And by a K algebra, I will always mean an associative algebra with one, but which is usually non-commutative. It could be commutative, but we are mainly interested in the case where it is non-commutative. And then we write capital mod A for the category of all right A modules. And we have its unbounded derived category. So it's the derived category whose objects are all complexes of all A modules. And morphisms are obtained from morphisms of complexes by formally inverting all quasi-isomorphisms. And well, if we want to deal with Hochschild homology, we need not just modules over A, but bimodules over A. So we introduce the so-called enveloping algebra. A tensor its opposite algebra. So the modules, the right modules over this enveloping algebra are precisely the A bimodules. For example, the algebra itself, of course, becomes a bimodule over itself for the natural action on the left and on the right. And we call this the identity bimodule because tensoring over A with this bimodule is the identity functor up to isomorphism. And then Hochschild, the quickest definition of Hochschild homology of A is to say it's the torsion functors over AE of A with itself. That's the torsion spaces of the identity bimodule with itself. And concretely, we can define it also as the homology of the Hochschild complex. I will denote the Hochschild complex itself by HHA and its homologies by HH lower star A. And here you have the picture of the Hochschild complex. This is in degree 0, then in cohomological degree -1, -2, -p+1. And well, we have the standard differential. So the last differential is just the commutator, and you can guess the higher differentials or look them up in any reference on the subject. And in particular, we see, well, if we look at zeroth homology, then we get the quotient of the algebra A by its subspace generated by all the commutators. Okay, so we get this so-called base space. Then a second important remark, of course, is that this complex is functorial in the algebra A, and therefore its homologies are also functorial in A. And we will consider the complex itself as an object of the derived category of K vector spaces. And of course, it is functorial as an object in this derived category, since it is even functorial as a complex. Okay. And then it will be important for us to extend these definitions from K algebras to K categories. And this can be done without any problem. So for example, the Hochschild complex then becomes replaced by this complex. So instead of the algebra itself, we write the sum of the endomorphism algebras of all objects. Then instead of A tensor A, we write the sum of these tensor products taken over all pairs of objects. And we should imagine the decomposable tensors here as diagrams. We have an object A0 and we have an object A1. We have morphisms going back and forth between these two. And then this same formula still makes sense, only that now A composed with B is an endomorphism of A0 and B composed with A is an endomorphism of A1, but the difference still makes sense as an element of this infinite, usually infinite direct sum, where it could also be finite, of course. And then similarly here, the decomposable tensors should be viewed as triangles like this, and well, the natural differential makes sense. Okay, and of course, yes, so a K category is just a category whose morphism sets are endowed with vector space structures such that the composition is bilinear. So in particular, we can look at a one object K category, and that is just the same datum as that of a K algebra. And then this complex generalizes the classical complex. And then, okay, one category to which we can apply this construction is the category of finitely generated projective A modules. That's a nice K category, essentially small K category. So we can form this complex. We get a well-defined Hochschild homology, well, Hochschild chain complex. And well, we have the inclusion of the one object category A into its category of projective modules, and this inclusion of this one object category into this infinitely many object category induces a morphism, and this morphism is a quasi-isomorphism. It's an isomorphism in the derived category, and well, this gives then a proof of Morita invariance of Hochschild homology, because the category of projective models is, of course, invariant under Morita equivalence, of course, up to equivalence. Okay, and now it will also be important to extend the definition once more from K categories to differential graded K categories. So, well, a differential graded K category is just given by a class of objects, and the set of morphisms between any two objects is now a complex of vector spaces. And composition defines a morphism of complexes from the tensor product of two complexes to one single complex. And here we have a typical example. We can look at the category of bounded complexes of finitely generated projective modules, and it carries a canonical structure of differential graded category. So we have morphism complexes. So when we have P and Q, two bounded complexes of finitely generated projective modules, we define the morphism complex in this way. The nth component of this complex consists of all A-linear homogeneous maps from P to Q, homogeneous maps of just Z-graded objects. So these do not take into account the differential. They're just homogeneous map of Z-graded objects. And then the differential is of these complexes is taken into account in the differential of this morphism complex. The differential of the morphism complex is just the commutator with the differentials of P and Q. And then you can easily check that indeed we get a differential graded category. The composition in this category satisfies the Leibniz rule, or equivalently, composition defines a morphism of complexes from the tensor product to the target complex. Okay, and well, when we have such a category, we can look at the H0 category of A. Yes, the H0 category of A is a K category, which has the same objects as A, but where now the morphism spaces are just the H0s of the morphism complexes. And you see that, well, if you take this complex and you take H0 of this complex, well, what do you get? You get cycles. Cycles are just morphisms of complexes. Yes, they have to commute with the differential. And you go modulo boundaries, and the boundaries are just the null homotopic morphisms from P to Q. So you find that the H0 category of this differential graded category is nothing but the bounded homotopy category of finitely generated projective modules. Okay, yes, so this is an important example of a DG category. And then, well, of course, this DG category contains the category of projective modules as a subcategory, now considered as a DG category concentrated in degree 0. And this inclusion induces a morphism between the corresponding Hochschild complexes. And this morphism is again a quasi-isomorphism. So it becomes an isomorphism in the derived category of complexes. And then from this, one can deduce the derived Morita invariance of Hochschild homology. Yes, how do we deduce it? Well, if we have our two derived categories of two algebras, A and B, and we have a triangle equivalence between them, then by using the results of Rickard from 89, we can deduce a zigzag of quasi-equivalences between these two DG categories. And this zigzag of quasi-equivalences is in fact, well, quasi-equivalences are in particular Morita functors. So actually we get a zigzag of Morita functors and therefore an induced isomorphism in the Hochschild complexes. Okay. Now, for a DG category itself, yes. So okay. So this was an example, and now I would like to state a general theorem which tells us how the Hochschild complex behaves when we have an exact sequence of DG categories. So I have to define what an exact sequence is. And for this, I need to define the derived category of a DG category. So let's take a DG category. And we define C of A as the category of differential graded right A modules. Yes, so for example, this DG category could have a single object whose endomorphism algebra is concentrated in degree 0. And then the DG category is just the datum of this endomorphism algebra. So it is equivalent to the datum of an ordinary algebra. And then this category C of A just becomes the category of complexes of right modules over the given ordinary algebra. So this generalizes the classical category of complexes. So what is a DG right A module? In general, it's just a DG functor from the opposite category of A to the DG category of complexes of vector spaces. And then, well, it's easy to define a natural notion of morphism of right A modules and a natural notion of quasi-isomorphism. That's just component-wise quasi-isomorphism. And then the derived category is defined by formally inverting all quasi-isomorphisms. And now I can state the localization theorem. So we take three DG categories, A, B, C, and we suppose that we have an exact sequence. And this means that the DG functors here induce an exact sequence in the derived categories. And so that simply means that the first functor induces an equivalence from dA onto a full triangulated subcategory of dB, and the quotient of dB by the image of dA naturally identifies with dC by the functor induced by this DG functor. Okay, so we will see examples in a moment. And then the theorem says that under these assumptions, we get a canonical triangle in the derived category of vector spaces. And in particular, well, if we apply homology, then we get a long exact sequence in Hochschild homology, linking the Hochschild homologies of these three DG categories. Okay, now let us consider, yes, so this will be one of the important ingredients for the computation of Hochschild homology of singularity categories. Now there's a second important ingredient, which is the behavior of the Hochschild complex under causal duality. Okay, well, let's assume that we have an admissible quotient of a path algebra. So we have a finite quiver, and we look at an ideal in the two-sided ideal in the path algebra, which is admissible in the sense that it's contained in the square of the ideal generated by the arrows, and it contains some power of the ideal generated by the arrows. And so in particular, the quotient will be finite dimensional because all sufficiently long paths vanish in this quotient. Okay, and then a theorem by Michel van den Berg from 2015 tells us that the Hochschild complex of the causal dual of our algebra A is the dual of the Hochschild homology of A, just the K dual. Okay, so what is the causal dual? The causal dual is just the derived endomorphism algebra of the sum of the simple modules. So in other words, we take the algebra A, we divide by the radical, which coincides with the ideal generated by the arrows under our hypothesis. And then we get a certain semi-simple algebra, actually just a product of copies of the field. It's this sum of all the simple A modules, and we take the derived endomorphism algebra of this sum of the simple modules. Yes, in other words, we replace R, say, by a projective resolution, and then we take the endomorphism algebra, the DG endomorphism algebra of the projective resolution. That gives us the derived endomorphism algebra. So this is a certain DG algebra. Our constructions apply to this DG algebra, and Hochschild complex of this DG algebra is the dual of the Hochschild complex of the algebra we started with. Okay, here is a small and very simple example. We take for our algebra A, we take the so-called Beilinson algebra. Yes, so it's given by this quiver, just with the commutativity relations. Then it's easy to compute the causal dual. It's given by this quiver with arrows which go in the opposite direction and are of degree +1 and satisfy anti-commutativity relations. Then Hochschild homology of A will be canonically isomorphic to the dual of Hochschild homology of the causal dual. And well, in this case, Hochschild homology itself is concentrated in degree 0 and just given by 3 copies of K. So maybe it's not such an exciting example from that point of view, but well, it illustrates the computation of the causal dual. Okay, and now we can look at Hochschild homology, first of derived categories and then of singularity categories of finite dimensional algebras. So we can take again an admissible quotient, and we look now at the finite dimensional right A modules and at its bounded derived category. So the objects are now bounded complex of finite dimensional right A modules. And among these, we have the complexes, the bounded complexes of finitely generated projective A modules. So this is just the thick subcategory generated by the free module. It's also called the perfect derived category. So it's a thick subcategory in the bounded derived category. And then one defines the singularity category as the Verdier quotient of the bounded derived category by the perfect derived category. And this type of quotient was first considered by Buchweitz in a recently published manuscript from 1986. And then it was rediscovered in a geometric setting by Orlov in 2003 with motivations from mirror symmetry. And now, when we are in this situation, then one can check that we get a canonical exact sequence of DG categories in the sense of the theorem which I've just cited. Yes, so we have the derived category, and the derived category actually has a canonical differential graded enhancement. It's the H0 category of a canonical DG category, which I denote by this symbol with the index DG. And the perfect derived category, well, it's a full DG subcategory. And then one can form the so-called DG quotient or Greenfeld quotient. And if we take the H0 categories, then we get exactly the sequence which defines the singularity category as the Verdier quotient of the bounded derived category by the perfect derived category. Okay. So we get a sequence which is exact in the sense which I defined before. If we look at the derived categories of these three categories, we get an exact sequence, a Verdier localization in the derived categories of these. And therefore, by the localization theorem, we get a triangle in the derived category of vector spaces. So in this triangle, well, here we have the Hochschild homology of the perfect derived category viewed as a DG category. And by, if you like, by Morita equivalence, this is just isomorphic to the Hochschild complex of A itself. And so this is isomorphic to the shift Hochschild complex, and it remains to compute this thing if we want to compute this thing. And how to compute this thing? Well, the theorem, first theorem, is that Hochschild homology of the derived category is the dual of Hochschild homology of A. So this is actually dual to this. And how can we prove that? Well, we have, if we look at the derived category, we can look at the sum of the simple modules, and the sum of the simple modules generates the derived category. And therefore, the derived category is equivalent to the perfect derived category of the derived endomorphism algebra of the sum of the simple modules. So this generates the derived category. We look at its derived endomorphism algebra, and we get an equivalence between the derived category and the perfect derived category over the endomorphism algebra. And then by Morita equivalence, Hochschild homology of the derived category identifies with Hochschild homology of this perfect derived category. And again, this gives us Hochschild homology of the causal dual, and therefore the dual of Hochschild homology by Vandenberg's theorem. Okay, and so in this sequence, we now know two of the three terms, namely this term, which is just Hochschild homology, and this term, which is just the dual of Hochschild homology. And now we can use this to compute this term, Hochschild homology of the singularity category. And what we get is that Hochschild homology of the singularity category with its DG enhancement is canonically isomorphic to what one can call the double Hochschild complex of A. What is the double Hochschild complex? Well, in degrees -1, -2, etc., we place the classical Hochschild complex. And in degrees 0 and greater than 0, we place the dual of the classical Hochschild complex. And then we have a link between the two, which is given by a map Tor, which we can call the trace map. Yes, so we have to define what Tor does. Yes, so it should go from A to the dual of A. So it is given by a bilinear form. And this bilinear form, yes, so we have to define what Tor of A evaluated in B is. And that's just the trace of the map given by left multiplication by A and right multiplication by B. Yes, A, remember A is finite dimensional, so left multiplication by A and right multiplication by B gives us an endomorphism of this finite dimensional vector space, and we can take its trace, and that defines this morphism which connects Hochschild homology with its dual. Okay, so the subtle point is to check that this is indeed the case. And then, well, if we take this description of Hochschild homology complex of S, we can pass to homology, and then we get dualities between, well, for example, homology here and homology here. These are these dualities, and then homology in degree +1 identifies with the dual of homology in degree 0. And this, so I have stated this for ordinary algebras concentrated in degree 0 of finite dimension, but one can generalize it to a suitable class of proper DG algebras, so DG algebras which have finite dimensional total homology. Okay. Okay, so we have successfully computed Hochschild homology of such a singularity category. Well, computed in the sense that we have reduced it to Hochschild homology of the algebra itself. And now I would like to apply this to give a computation of Hochschild homology of Leavitt, the Leavitt path algebras. Leavitt path algebras are certain infinite dimensional algebras associated to quivers. And this works as follows. So we start from a finite quiver Q. Yes, we could just start with the quiver with one vertex and one loop at this vertex called epsilon. And then we look at the associated radical square 0 algebra. So we divide the path algebra by the square of the ideal generated by the arrows. So in this example, we just get the algebra of dual numbers. And now let me sketch the construction of the Leavitt path algebra. For this, we write Q upper star for the opposite quiver, but where we give a degree to the arrows. The arrows are now all of degree +1 in this opposite quiver. So it's a graded quiver. Each arrow has an integer degree. So in this example, well, we can just get a loop, but now the loop is of degree +1. Okay, so that's the first step in the construction. And now, as a second step in the construction, we fix a vertex of our quiver, and we look at all the arrows going out from this vertex. Yes, all the arrows going out from I in the opposite quiver. So we number them from 1 to ni for some integer ni. Okay. And we write pi for the projective module associated to the vertex. So it's actually a z-graded projective module over this z-graded path algebra. And now we look at the morphism from the projective pi to the sum of the shifts of the projectives associated with the targets. Yes, for each such arrow, we have the target, and we can look at the projective in this target, and alpha star multiplication on the left by alpha s star defines a morphism from pi to this graded projective model shifted by 1 degree to the left. Yes, sigma is just the shift by 1 degree to the left, also called suspension or denoted by bracket 1. And yes, so if we look at this matrix of left multiplications, we get a morphism from this projective module to this projective module. So in our running example, we only have one such morphism. It goes from P1 to the shift of P1. And notice that, well, if the vertex number I is a sinc, well, then there are no outgoing errors, and then this sum is just 0. Okay, but that's not a problem. Yes, I mean, sometimes people assume that the quiver we start with doesn't have sources, so that Q star doesn't have sinks, but we can allow sinks, we just have to define the sum to be 0. Okay, and now what we do to get the Leavitt path algebra is, well, we look at a formal inverse of this morphism between projectives. So we formally adjoin, and yeah, if you like, we take our category of finitely generated projectives and we formally adjoin an inverse for each of these morphisms phi I. And we, okay, these are morphisms from a direct sum to some projective modules. So they are given by matrices, row matrices with certain components. And these components have to satisfy the relations which tell us precisely that this matrix is inverse to this matrix. So these are the relations which we impose on these betas. And then the Leavitt path algebra is just the path algebra, the graded path algebra of the opposite quiver Q star, where we adjoin all the coefficients of these formally inverse matrices. Okay, so it becomes a path algebra divided by some ideal, but this ideal, so the ideal expresses that these two matrices are inverse to each other, and of course it's not an admissible ideal. But anyway, we get this Leavitt path algebra, which is almost always infinite dimensional. In our running example, this Leavitt path algebra, well, we just have to adjoin the formal inverse of alpha star. So we get the Laurent polynomial algebra in alpha star and its inverse, where alpha star is of degree +1. So we take this Leavitt path algebra and we endow it with the zero differential, then it becomes a DG algebra. And this DG algebra has a categorical meaning, namely by a theorem which originally goes back to Paul Smith from 2012, and then it was further worked out by Xiao-Wu Chen and Yang in 2015. So the meaning of this algebra is that it describes the DG singularity category of our radical square zero algebra. So remember, A was the radical square zero algebra associated with the quiver Q. And so we can look at the singularity category of this radical square zero algebra. And the theorem tells us that we can also describe it as the perfect derived category of this DG algebra with vanishing differential. Yes, the graded Leavitt path algebra with vanishing differential. And the equivalence send the ith projective module to the ith simple module in, okay, considered as an object in the singularity category. Yes, remember, this is the quotient of the derived category by the perfect derived category. In particular, well, every module is a complex concentrated in degree 0, and therefore it yields an object in this quotient. Okay, and so now as a corollary, yes, we have such an equivalence, and it yields an isomorphism in Hochschild homology. So we already know how to compute Hochschild homology of this singularity category. It's computed by the double Hochschild complex, and therefore Hochschild homology of the Leavitt path algebra is also computed by the double Hochschild complex of our algebra A. And since it's a radical square zero algebra, one can actually make the computation quite explicit. And as a first corollary, one gets that the Hochschild homologies of these Leavitt path algebras are finite dimensional, yes, which is not clear a priori. And when one makes it explicit, then one can check that what one gets coincides with another computation of Hochschild homology of Leavitt path algebras, which is due to Pereira and Guillermo Cortinas in proceedings of the AMS in 2015. So we get yes, so they have a completely different method for computing Hochschild homology. Okay, and now in the remaining few minutes, I would like to, so this was all for radical square zero algebras, and now I would like to go beyond radical square zero. So now we take a finite quiver and some admissible ideal, and we have the algebra A, quotient of the path algebra by the admissible ideal. And we have an associated radical square zero algebra. Yes, if we write J for the radical of this algebra, then the algebra decomposes as the sum of the simples plus the radical. And we define a new algebra A0 by taking the tensor algebra over the radical modulo the square of the radical in the tensor algebra. So this is the radical square zero algebra with A. Yes, it is as a vector space and even as an R bimodule, it is the same as A. But well, in the algebra A, when we multiply two elements in J, we get something which is usually non-zero. Whereas if we multiply two elements of J in A0, then we get 0 by construction. So A0 is a radical square zero algebra, and we can think of the original algebra as a deformation of this radical square zero algebra. Yes? Here we have trivial multiplication, here we have non-trivial multiplication, yes, which is obtained by slightly deforming the trivial multiplication in A0. Okay, and now the idea is that such a deformation should correspond to a deformation of the corresponding singularity categories. This is the idea of Xiao-Wu Chen and Zhengfang Wang. And well, we already know that the singularity category of the radical square zero algebra is described by a Leavitt path algebra, LA0, as associated with this radical square zero algebra A0. And so the upshot is that this singularity category should also be described by some version of the Leavitt path algebra, which should be a deformation of the Leavitt path algebra of A0. Okay, this is all just heuristics. The deformation theory of DG categories is not well understood for the moment, but well, it looks quite plausible and it turns out to be feasible. So although this deformation theory is not well understood, what Xiao-Wu Chen and Zhengfang Wang show is that indeed, if we take this Leavitt path algebra, we can find a usually non-zero differential in such a way that if we take this DG algebra, then it describes the singularity category of the algebra A, which is no longer a radical square zero algebra. So here we have zero differential, and we've deformed the zero differential to some non-trivial differential here, and we get the equivalence which we hope for. And then, by the same argument as before, we can compute the Hochschild homology of this differential graded Leavitt path algebra it is again given by the Hochschild complex of the finite dimensional algebra A, which of course now is usually much harder to compute than in the radical square zero case. And yes, and I would like to finish here. So thank you very much for your attention.
Thank you very much, Bernhard, for your interesting and beautiful talk. Well, let's send him a big applause.
Thank you very much.
So now we move to the questions section. We normally begin with questions from the online audience. So if any remote participant has a question, just feel free to unmute or to write your question in the chat room. From the online participants.
I have a question, if it's possible.
Yes, yes, please.
Oh, thank you. Well, first of all, thank you for the nice talk. It was very interesting and really inspiring.
Thank you.
So I have a question coming from what I tend to think about the singularity category, and I think of it often as kind of like the stable module category, right? When you have this.
If the algebra is the algebra is self-injective, then it is exactly that. Yes.
Right. Right. So. So one of the questions, one of the ideas behind this this stable module category is the computation of the Tate cohomology.
Yes.
Which in general is hard to do for any ring because you have for the construction itself you have to have very specific conditions. Yes. So here is this. So I kind of forgot where you had it, but this Hochschild cohomology and the dual. And and you perform the computation. So essentially my question is if this is kind of like an analogous to what the Tate cohomology should be.
Yes, I mean the link to Tate cohomology is the following. If you imagine that you have a self-injective algebra, and then the Tate cohomology of the sum of the simple modules will be the endomorphism algebra of the generator. So actually, if you like, in this setting, what appears as Tate cohomology is the graded Leavitt path algebra. So the graded Leavitt path algebra plays exactly the role of Tate cohomology. And in the radical square zero algebra case, it is very nice and easy to compute. And that's why we can find that it is actually the Leavitt path algebra. Yes.
That's very nice.
For the question. Yes.
Thank you.
Thank you, Daniel. Any other online question? So it seems not more. So in-person audience, any questions for Bernhard? I have one. I was wondering if one can follow, let's say, a dual approach to obtain similar results in Hochschild cohomology.
In Hochschild cohomology. Yes, Hochschild cohomology behaves in a very different way. Yes, there is no long exact sequence for Hochschild cohomology. Yes, what can one say? Yes, so one can look at Hochschild cohomology as well, of course, and it turns out that you can show that Hochschild cohomology of the singularity category is isomorphic to what is called singular Hochschild cohomology, namely the endomorphism algebra of the identity bimodule in the singularity category of bimodules. Yes, maybe I can share the screen and show what I mean exactly. Yes, so on the one hand, we can look at Hochschild cohomology of the DG singularity category, and on the other hand, well, maybe first in the classical case, we know that Hochschild cohomology of the algebra A, we can also compute it as the Yoneda algebra in the category of bimodules of A with itself, because this is essentially due to Cartan-Eilenberg. And here, there is something analogous, namely, we can show it is isomorphic to the Ext in the singularity category of bimodules of the algebra with itself. Yes. So notice that this is non-trivial. This is not just the definition. Yes, if you want to compute Hochschild cohomology of this DG category, you have to write down the Hochschild cochain complex for the DG category, which will be an enormous object. And here, well, you just have to write down. You just have to do a computation in the singularity category of bimodules of this bimodule with itself.
Okay, I see.
Yeah, there seems to be some problem with the audio.
Okay, thank you. So let's thank Bernhard again.
Thank you very much.
Bernhard. The invitation is for next week, next Friday, where we have Professor Maria Julia Redondo, and we will send you the information about the talk, the title and abstract next week. We hope to see you then. Thank you very much.
Thank you once more for the invitation. And
thank you, Bernhard.
See you at some other opportunity, hopefully in person. Bye-bye. Thank you.
Bye-bye. Thank you.
Bye-bye.
Thank you. Goodbye, everyone.